So I'm Smita Krishnaswamy. I'm from Yale. I have kind of an interdisciplinary background. I was trained basically in computer science and also some amount of applied math, especially in undergrad and master's. And then I was at IBM writing algorithms and some AI methods for automatic generation of large logic networks when I was like, I just don't want to do this anymore, and I want to have impact on health and biology and stuff. And so I wrote to Donna Peer, who's her colleague, while I was sitting on a train to Boston, like, okay, can I come work in your lab? And to my huge surprise, she instantly responded. She's like, yes. But you're going to get a salary cut by, you're going to get your salary cut by 62%. And it was worth it. Of course, that was like terrible salary for New York City, but still worth it. So that I just gave you that little spiel just because I just wanted you to hear where I was coming from before I give this talk, which may be a little more methodsy than a lot of talks you've heard at this thing. But I'll go ahead and start. As you guys all know, biological systems are highly complex systems, and in a very canonical sense, because they have a lot of interacting components, and you want to figure out what's going on. And the question is, now we have all this data, can somehow adding machine learning to all this data really help? And to help figure out the answer to this question, I actually asked DALL-E, and DALL-E generated this wonderful image, which I augmented with something. So basically, as you guys have heard from people, even at this lab, you can't just stick scientific data into neural networks and actually expect it to give sensible results about what's going on, mechanistic understanding, and so on and so forth. And basically today, I'm going to tell you that you can actually infuse neural networks with more structure that can help them discover more science. And this structure is in the form of geometry, which graphs are an embodiment of, but also about what the signals in these data sets are like and what biases can capture them. And so that's kind of the idea of the rest of this talk. So if you want to look at a place where, especially, I'm sort of largely talking about machine learning, but focusing on deep learning. If you want to see somewhere where deep learning has had a lot of success, it's in computer vision, and especially in natural image processing. So these are naturalistic images, and computers or deep neural networks, convolutional neural networks, have been very good at classifying them, generating them, so on and so forth. You saw DALL-E is also doing that. I could do it from a prompt, as you saw. One of the key ingredients there is that you have a lot of clean data, and that's one of the missing ingredients in biology. Our data is not clean. And a lot of the data is missing. The other thing is that actually convolutional neural networks, if you think about how they work, they're really taking advantage of some structure in the data. So convolutional neural networks, they work on images, and images actually have this wonderful structure. They're a 2D grid. You know exactly how to slide over them. Whatever you're looking for, you basically look for everywhere. So there's a kind of translational invariance there. So that means if you're classifying images of cars, you don't care exactly how the car is positioned. It can be anywhere. And because you have a lot of clean data, and we have these methods that actually mathematically take advantage of this structure, that's really why they work on that. So basically the idea is, can we mimic this in data that is not structured like an image, for example? Okay, so the issue is if we only had images and we wanted them processed in a similar way to natural images where we're just detecting objects in the images, then CNNs would be fine. We wouldn't have to build anything new. But we usually have what are called unstructured data types. So these would be these point cloud data sets. I think this is a UMAP plot of some single cell data. You see it's kind of an inchoate blob. And then you can have irregularly structured data types, which you might also be familiar with, things like molecules where the bonds have different angles and lengths and these kinds of things. So what do we do with these kinds of data? The basic answer is you have to build in the kind of structure that CNNs had for images. Okay, so the first thing we do to induce structure in it is to actually structure them as a graph. So you have an intermediate representation of these objects as a graph. And it turns out that graphs have some kind of structure and they're simple, but they're also very, very flexible. They could be used to model almost anything. So here's some biological type examples. Any kind of interaction can be modeled as a graph. So these are social interactions. These could be your Facebook friends. In molecules, you have bonds and interactions via bonds, chemical bonds. Gene regulatory networks, these are gene-gene interactions, so maybe transcriptor and factor to target. So anytime you have interactions, they can easily be modeled as a graph. You can also model physical adjacency as a graph, and you actually saw a beautiful example of that in James's talk yesterday. He was modeling, these are cells that are flashing calcium, and he had a cell-cell adjacency graph. So physical adjacency can be modeled as a graph. So you could turn an image into a graph too, just connect the neighboring pixels. And sometimes you do that just to make sure your graph algorithm is working. But also complete point cloud data, like I showed, can be turned into a graph. And this is a technique that's used in a lot of the manifold techniques from my lab and other people's labs, like Ritambra's lab. So here you have cell by gene data, for example, and then you use some kind of distances to turn from cell by gene to cell by cell. So now it's a distance matrix. Sometimes that actually reduces dimensionality because you have more features than you do data. Sometimes you don't, but it's okay. And then the important thing is these distances are not the intrinsic distances that represent the whole graph. So you have to make sure it's connected locally. So you pass that through an affinity. And this affinity matrix you can use in place of the graph adjacency matrix. And the way you turn a distance into an affinity is by passing it through a kernel like this, which zeroes out or pushes close to zero, far away things. And if something's very close, it's close to 1, and you get something like a soft nearest neighbors graph. So any of these things can be turned into graphs, and now the question is, can we process these things on graphs? So one more example that I've actually been using is, I've actually been using a knowledge graph lately that's called SNOMED. It's actually a fantastic knowledge graph. So the reason knowledge can be a graph is because the embodiment of knowledge a little bit is set theory. So if something is an example of something else, then there could be a directed edge there. You could also model it undirected sometimes. So any kind of knowledge graph, knowledge concepts, relationships between concepts is also a graph. So anyway, so now that we model these on a graph, we have to translate these ideas from CNNs to graphs. The first idea is this idea that you have a local receptive field. So in CNNs, you have this convolution operation that I'll show more in a second that slides through the thing. So how do you do that? Graphs are irregularly structured, so there's no easy way of sliding over a graph, but I'll show you how you try to do it anyway. Once you have that, you check the same thing at every place. That's easy, you just share weights. And then pooling is summarizing the information, and you can do that by averaging or pooling over things in the graph, for example, if you want to classify the graph. Okay, so the convolution operation very precisely looks like this. You're basically shifting over the graph, and you're taking this filter that you've designed, and you're pointwise multiplying and summing up the results, and the results getting stored there. And what that's doing is saying, I have a signal or feature that looks like this, and I want to see if I can detect it in the image. So it's convolving over the image. And this is the convolution operation. So on graphs, the way convolution is done is to look at a neighborhood around a vertex. So you look at a neighborhood around every vertex, so you've slid things along the graph somehow. But it's not as easy as striding over an image. And there's some difficulties with it, but you can sort of do it. So GNNs use this particular idea, and then they just sum up coefficients in a weighted sum. So they're kind of taking a literal version of this spatial kind of convolution. So what they can do is they can take a feature to these neighboring vertices, and then they pass it to their neighbor. So B gets signal from A and C, or it gets a message from A and C, and it aggregates it. The aggregation is usually a weighted average or a mean. And after it aggregates it, it takes the original feature that was on the point itself, and then it can update it. And so the update can be sort of an activation function or a nonlinearity. This is how GNNs work. But unfortunately, GNNs are not very powerful. It turns out that you can't make GNNs deep like CNNs. CNNs you can make 50 layers deep, and they'll continue to improve. But GNNs, what they're actually doing is they're just smoothing stuff. They're like taking local averages. So if you do it 3 or 4 iterations, every point has talked to every other point. Now they all have the same information, and they all look identical, right? So this is a big drawback of GNNs, and they make them strictly less powerful. But so they're not approaching the kinds of power that CNNs used to have, right? And another problem is if you don't do that, then they're not reaching very far. They're just doing reasoning about local stuff. So they can't reason about an entire molecule. So you have to have that trade-off, under-reaching or over-smoothing, okay? So my kind of solution to this, or the one that I'm developing, has to do with, first off, convolution comes from signal processing. So can we take more ideas from signal processing to fix this? So I'm not the only one that's had this idea. People who wrote stuff like GCN, like Jean Brunat, are actually from signal processing labs. Jean Brunat is from Stéphane Malat's lab, who's a prominent signal processor. So this idea has been had before. So the idea is if you had audio signal and you had these signals, then there's other stuff you can do. So you can Fourier transform the signal. That means you can get Fourier coefficients by basically integrating it with waveforms of certain frequencies. So you can take a signal, you can Fourier decompose it, and you'll get its constituent frequencies, and you get a frequency domain representation. Okay, so usually you don't have the full functional form available, so usually what people use is the discrete Fourier transform, where you're looking at these discrete coefficients. So you're looking at just the integer multiples k, 2 pi I k over n, and you're taking, instead of an integral, a summation of your signal, and that gives you a coefficient. So this turns out to be a linear operation, and you can make it very, very fast. So that's why Fourier transforms and fast Fourier transforms are used all the time. And they give you a different kind of representation where you can do more than just local averaging, which is a low-pass filter. Okay, so you can convolve with any filter in the Fourier domain. So that means you can convolve, for example, with this kind of filter, and you get this other new signal. And it turns out the reason it's very easy to do in the Fourier domain is this kind of convolution is just pointwise multiplication in the Fourier domain. So convolution in the time domain is just pointwise multiplication in the Fourier domain. Okay, and so you can use this to create all kinds of interesting filters. The one that GNNs naturally have is a low-pass filter. So we can also create band-pass filters, high-pass filters, all kinds of filters. So I was just highlighting low-pass because low-pass filters are the ones that smooth. So if you can use those just for denoising, but they will give you a smoother version of what you previously had, or a more sort of dithered version. So now can we translate these to graphs? So now you think of the features on a graph as a signal that's flowing through the graph, much like space or time. So the way you do a graph Fourier transform is using a matrix that's called the graph Laplacian. The way that's computed is by taking the adjacency matrix and then subtracting that from what's called a degree matrix. This is just the sum of this row put into the diagonal that corresponds to that row. So diagonal degree matrix. So for example, vertex 1 has degree 2, so you have 2 in that entry. Vertex 2 has degree 3, 1, 2, 3, etc. So subtracting these gives you the Laplacian. There's many versions of the Laplacian, and it turns out you can use any of them. You can use a diffusion-based random walk Laplacian. You can use a normalized Laplacian. But the basic idea is the eigen decomposition of the graph Laplacian gives you your new Fourier harmonics on the graph. So these are the sines and cosines that you had in Fourier decomposition, but they're just placed over a graph. And so these eigenvectors are the so-called harmonics. And the eigenvalues are the squares of the frequency. So you get a frequency domain representation, and you can start doing more complicated kinds of filtering. So if you don't believe me, you can actually draw the eigenvectors of this line graph, and they actually look exactly like sines and cosines, with the low frequency ones taking small sweeps and the high frequency ones going up, down, up, down, up, down. Okay, so this creates a graph Fourier transform and an inverse Fourier transform. Because this is an orthonormal vector, you can just take its transpose to get the inverse, and then you can flip back and forth between time domain or graph domain, graph vertex domain, and frequency domain. Okay, so you can use these to create spectral filters, and they can be more sort of complicated than just the low-pass filters that I drew here. And so here can be signal and noise, and you can use a filter to remove the noise. So this is actually the concept by which graph convolutional networks work. But it turns out that a lot of them are fairly limited too, because they don't want to eigendecompose the graph Laplacian. That would make them very slow. So graph convolutional networks deal with a graph Laplacian, but they want to design filters that are just polynomials of the graph Laplacian. And it turns out that if you have polynomials of the graph Laplacian, that somehow restricts the operations you can do. Moreover, they usually restrict its operation to a one-hop neighborhood, and then you're underreaching again. So this is why graph convolutional networks, they have an interesting idea, but they're still applied in a limited fashion. So usually you can use a polynomial of your Laplacian called a Chebyshev filter, and then so you're getting combinations of these kinds of shapes. But they are something, and they can be used for some problems that GNNs can't be used for. So let's go at it again. Let's use more signal processing. Okay, so in signal processing, not only do you have your Fourier decomposition, you have wavelets. Wavelets are really fantastic because they localize things in time and frequency. So they're like a little blip or an oscillation, and you can stretch them, squish them, okay, and you can also shift them. So that can give you another kind of decomposition that's called a discrete wavelet transform that can describe spatial and frequency characteristics of your signal. So you have equivalent discrete wavelet transforms here, and they're continuous and discrete counterparts. And wavelet transforms can also be useful. And it turns out that we can create wavelets on graphs using graph diffusion. So if you have a signal here, you can see that diffusion of this signal is a Dirac. You can diffuse it, and you can see the difference between 1- and 2-step diffusion can mark several different vertices here. So it can give you a lot of information about what's at how far from what else. So that's giving you kind of some mix between local and global information, and it is not just a low-pass filter. Okay, so you can create a diffusion operator from a graph just by taking the adjacency matrix and dividing out by that diagonal degree matrix. So that gives you the diffusion operator. You can use the diffusion operator and subtract 2 scales of diffusion with some laziness, and that creates what's called a diffusion wavelet on a graph. So the interesting thing about great diffusion wavelets is instead of looking at instead of either smoothing or looking at global characteristics, they can pick out very specific bands of signals, and it can be more informative about how your signals are spread on the graph. So we've been using these by putting them into graph neural network by something that's called learnable geometric scattering. The idea of geometric scattering is that you take a cascade of wavelet transforms that are arranged deep, because you want to create a deep neural network in a way that GNNs can't be deep. This is called a scattering path. And then at each step after you take the wavelet transform, you take an absolute value, nonlinearity, and you can actually replace that by a different nonlinearity like neural networks have. So it's very similar to neural networks where you aggregate signals based on the waveform, and then you take a nonlinearity. But it turns out in scattering you could just use absolute value. And then what you do is now you have representations over every node. You've placed Diracs on them, you've let them diffuse to different scales, and you've taken their the wavelet transform based on that of some signal that's on your graph, based on these wavelets that are centered at every vertex. And then you've aggregated them to create node embeddings, and now you can aggregate them further using statistical moments to get graph embeddings. So it turns out that you can have a very designed version like this, and you can use all the bells and whistles of neural networks to relax it. So we've relaxed it to learn the scales of wavelets, to learn a nonlinearity, to learn a graph level aggregation function. And you can even go all the way back to your adjacency and say, oh, my adjacency is not quite right. I can backpropagate all the way through to my adjacency. So basically, LEGS has 3 modules. It has a diffusion module that gives you the different scales of diffusion. It has a selection module to get subtractions between scales that we learn to make those wavelets. And it has a scattering module that aggregates all these things. And then you get different scales of diffusion. And you can repeat this entire construct again to go deeper and deeper and deeper. So it turns out that this has permutation invariance the same way you want graph neural networks to. I'll skip over that. So I just want to show you a couple of examples. So we've used learnable geometric scattering in an autoencoder setup. So in an autoencoder setup, we put a whole bunch of molecules in. So here we had a graph, and we were mutating one edge at a time, so we should get a trajectory of graphs. And you see that if you're using something like a graph scattering, a graph autoencoder, or a graph VAE type technique, that sometimes it's not good at telling the exact shape of the data, how the trajectory looks. A more important example is this. These were molecular graphs of a non-coding RNA molecule that was a riboswitch. You can imagine a riboswitch has 2 kinds of conformation, it switches between them, and there's 2 lower energy states. So you can hardly see that with most other methods because graph representation methods haven't been very powerful. Whereas if you add the scattering together with the neural network layers, it's giving us a much better idea of what these families of graphs can look like. And then you can also use it to generate molecules. By traveling through the latent space, you can generate different but related molecules. So currently, we're using this to optimize molecules, for example. So our current framework is called Graph Scattering Synthesis Architecture. So it has learnable geometric scattering. It has that autoencoder path. But it also has a regression path for predicting properties of the molecule. It has a generation graph path that's adversarial for generating new molecules. And we're using that to generate latent, this is 80,000 molecules that our AMD collaborator panned for treating AMD, which is a retinal eye disease. We put that together with drug bank molecules and came up with an embedding. And the molecules that they started with are somewhere, but we can actually improve them by traveling in latent space in the direction of the gradient that goes towards higher fitness. And so, and because the latent space is an embodiment of the graph that's pretty faithful to the graph, you can generate it out as that graph again. So here we're also doing some mechanism of action thing. So if they found some hits and they have no idea why they work, we're looking at their nearest drug bank neighbors to see what they might have been tested for and what those mechanisms of actions might have been discovered to be in the lab. So these are just some ways we're using it. I started with point clouds of data. It turns out you can also make neural networks similarly for point clouds of data. You just use the method I told you to create the graph. And now we're taking entire data sets from melanoma patients and classifying between responders and non-responders by basically describing a point cloud. Usually it's very difficult to push a point cloud through a neural network. They're not all the same size, shape, or anything, right? But if you turn them into a graph and then treat the genes as signals on the graph, and you use signal processing, you can do it. So that's kind of the message. So that's basically what I wanted to say. The only additional thing is these turn out to be fairly much more interpretable because these are signals on the graph, and we can, from the wavelet transform, tell where the wavelet was localized that differentiated between the different classes. So a little bit more interpretable also. So that goes kind of hand in hand. Building structure in can lead to more interpretability. So that's basically what I wanted to cover about graph signal processing and how you can use it inside deep learning or other kinds of machine learning. So you could probably do this with a random forest as well. But I just happen to like deep neural networks. So that's the end of my talk. So you can let me know if you have any questions.